Good morning, and we will be finishing the theory of distribution part in a couple of lectures. Yes, there are plenty other things to do it, but naturally in a small course we cannot cover everything, but the important aspects of distributions are covered, which will be initially is good enough for you to study. So far we have introduced distributions, and we introduced two important concepts of the distributions of finite order in the last couple of lectures, and also we have seen the distributions with the compact support. So T of finite order, this we are introduced, and T compact support, these two notions we have already introduced. Not only finite order of a distribution also. First we have defined order of a T, and then finite order distribution, and T with the compact support. So in the process of introducing support, the support is a subset of omega. Okay, it is not support, is a, though D is defined on d omega. So the support is not a subspace or subset of d omega, that you keep it in mind. And we also seen that T is a distribution d omega to r. If it is a T is a distribution, it is from t omega to r. When T has compact support, you can extend this T to a bigger one space. Okay, this is nothing but your C infinity of omega. So if you use the same notation, so when you say that T is a compact support, T can be extended to you here as a continuous linear functional. Conversely, if T is a continuous linear functional here, then the restriction here will have compact support. So that essentially means that the distributions can be with the compact support can be identified with the E omega, and so since d omega is in this one, and you also have a topology, with that topology you also have this inclusion. These are the things which we have discussed, because if Phi converges to 0 in E omega, then that converges to 0 in d omega, and all that you can no, in d omega, then you get in E omega. So you will have, because E omega is a bigger space, so E prime will be a smaller space. So we will see one more result theorem. Proof is very thing, but it is subtle, the proofs are subtle, but not that difficult once you get an idea of distributions. So every distribution with compact support is of finite order. Every distribution with compact support is of finite order. So this basically means that distributions of compact support are identified this way, and this is contained in the finite order distributions, which is given by d f prime. Okay, and that is, these are all strict inclusions, and this will be in d prime. So you see, you have all these inclusions very clearly, nicely. So let me try to give you a proof. First let me give you the intuition, that is very clear. Intuition. What is the meaning of T? So take, suppose T is in E prime. The proof is one line, once you know the idea behind. So when T is a distribution with the compact support, you recall the continuity estimate. So a distribution has a continuous estimate, in that you have an estimate for which you have to prove that nk. So you have something like this, if for every distribution is in thing T of E is basically some constant which depends on a compact set and norm phi. This n depends on k. This is true for all phi with compact. So this is for every k there is a continuity estimate. So recall that, recall continuity estimate. So if you want to show that T is of finite order, you have to show that nk is to show that nk is equal to n independent of k. K if T has compact support. That is the theorem. Has compact support. Okay. So, look at the idea. So, let me take K1 equal to support of K1 equal to support of T, which is contained in omega compact. Okay. So, you have K1 which is in support. So, you have a domain omega. So, let me give you a picture, and for this K1, so you have a K1 here. So, this K1 produces n K1, that is by the continuity of T as a distribution. Of course, you have to get n independent of K1. Now, this is K1. Now, suppose K is here. K is here. Suppose K is contained in K1. Then immediately this you know, this implies as bigger the compact set, your number will only going to increase, because if nk1, that is true. Reason is that nk is that many derivatives are needed. So, if you have bigger and bigger set, it is possible that you may need more and more derivatives to estimate, but so the compact set is smaller and smaller, you do not need it. So, that means nk1 will work, because if nk1 is bigger, nk1 will work for k as well, that is nk1 will work for k as well. That is very immediate from the continuities. Similarly, if k is outside a neighborhood, so you see, suppose k is an outside the k1, outside a neighborhood of k1, then k is not near k1. That means for every phi supported in k, T phi will be 0. Okay. Similarly, if k is outside a neighborhood of k1, outside a neighborhood of k1, then that will imply your nk will be 0. You can use that, because T phi will be 0. So, you do not need any derivative or anything to estimate, as T phi is equal to 0 for all phi with support phi in k. So, the only problem will come, let me use a color, the only problem will come if there is a k something like this intersecting. Okay. This is where whether it will contribute k, but you see k is little away from k1, from here essentially no contribution. If k is here, your nk1 will work basically. So, the only issue is something it can increase the you need in a neighborhood of that. So, you probably have to expand take a k slightly bigger than k1, and that should work for every phi. So, now let me complete the proof with that. So, this is our trick. So, you choose, that is all the trick, choose phi naught in d of omega with phi naught identically 1 in a neighborhood of k1. This is what you are, exactly what I said, to get that bigger k, neighborhood of k1, okay, and call it k2 is equal to, let k2 is equal to support of phi naught, and of course, this is contained in support of k1, and the claim is nk2, that is fixed, nk2 will work for all k, in the continuity estimate, in the that is all you want to prove it, continuity estimate. Okay. that is all it. So, how do we prove that one? So, K2 is nothing but support of phi1 contained in that one. So, since phi naught is identically 1 from our previous class observation, and phi and phi naught both having the same thing on K1 on the support in a neighborhood. So, this will immediately imply your T phi, this is the observation we already made, T phi is equal to T phi naught. Okay, because phi naught is 1 in the support, so it depends only on the support of T, because K is in K1, the K1 is the support of T. So, T phi, therefore, that implies modulus of T phi is same as modulus of T phi naught, and now observe that support of phi naught is contained in K2, okay, because phi naught support is K2, so it contained that. So, this is less than or equal to, by continuity estimate, to known phi naught in NK2. But note that now phi naught is a fixed element, and phi naught at the norm of that contains it is a kind you can apply Leibniz for d alpha of phi naught. You expand it and d alpha of phi naught can be estimated by a constant. All the derivatives can be L infinity can be estimated. So, you can combine that constant with you can, and this can be estimated by C some other constant that depends only on K2 and known phi at NK2. So, the proof is actually this one, nothing more than that, okay, and that is what that implies T is of finite order. Okay. So, I am going to prove, I am not going to prove this completely, I will give a sketch of the proof, and another important factor for all distributions with support 0 can be written as a linear combination of the Dirac delta, a finite mini Dirac delta. So, let me write the theorem and I will give you the again the previous one has the complete proof. This there is some analysis you have to check, which I leave it as an exercise or you can do it, but I will essentially give you all the ideas behind it. Okay. So, that is what we have proved. So, let T is in d prime of omega with the support of T is equal to 0. Then there are constants A alpha such that T is equal to sigma A alpha d power alpha of delta. Okay. So, that is it. You see, any distribution is order this thing. So, let me make the remarks, proof, probably sketch or idea, proof, sketch or idea. This is basically the proof is basically so the end yeah, there are constants alpha and an integer m, finitely integer non-negative integer m, this is mod alpha less than or equal to m. So, the first observation m, if star is true, so let me call it this is star, if star is true, then yeah, first observation is not that. First observation is a support of T is 0, since it is compact support, T is of finite order. T is of finite order. order. And then if star is true, then m has to be the order of t, because if m is bigger, the estimates needs a bigger derivative knowledge. If the estimate is works for smaller m, then small is enough. So, it cannot be anything different. So, if at all we are expecting that, the order of t has to be m. So, these are the two observations immediately make. Now, it is about the functional analysis. I will just remark, if you want, you can see this in Rudy reference. See Rudy. This says that if you have continuous linear functionals, finitely many continuous linear functionals, and then f can be written as the sum of fi's. Sum fi is basically says that the kernel of the intersection of fi should be contained in the kernel of f. That means if fi of phi vanishes for all phi in that or fi of x vanishes for all x, then fx vanishes, then you have this one. So, with this one, look at here, these are the now the idea you have to do that d power alpha of delta of phi is equal to minus 1 power mod alpha phi mod alpha of L basically at 0, you see. So, if phi is in the kernel, of d power alpha of delta, that implies your phi alpha is equal to 0. And what you have to prove? You have to show that if that is there, to prove that t phi is equal to 0, that is all you want to prove. So, under this assumption, for all mod alpha less than or equal to m, you have to want to show that your t phi is equal to 0. Then you are done. So, that implies phi is in the kernel of t. Okay. And now, it is a little bit of technical two points you have to understand. Now, you see that support of t is equal to 0. So, if you have take any phi outside a neighborhood of 0, t will not contribute anything to it. So, if you take a small, however small neighborhood and then take phi support, so the t phi, non triviality of t phi will come only from the neighborhood of 0 because of the support of 2. That is one observation. Second thing, phi mod alpha of 0 equal to 0, phi mod alpha of x will remain small in a neighborhood of 0. Okay. So, for all mod alpha less than or equal to m, phi mod of the alphath derivative of phi at 0 will remain to be small in a neighborhood of 0. And anything mod alpha the d alpha of phi greater than m, the mod alpha greater than m will not contribute to t, because t is of finite order in the estimate. So, with all that you can show that t of phi sufficiently, because t of phi will depend only on the derivative of phi up to order m in a neighborhood of the origin, and that means your t of phi will also be small. So, complete the proof with that. So, you have to write down that estimate complete, basically show that modulus of t of phi is less than or equal to epsilon for arbitrary epsilon. Show that is all. So, this is a very interesting thing where support of t you can really characterize that. So, the next thing now we one more typical thing, a couple of important things which are the localization and singular support. Localization and singular support. Singular support. You have seen the support. Now there is a singular support of t belongs to d prime of omega. So given omega, so suppose start with d in d omega, okay, and omega naught is a open set in omega. This is open. Okay. So want to understand basically how to, so you have a omega. So t omega and t is defined in d omega. So that t is defined for all functions in no, d prime. So t is a mapping so t is a mapping from d omega to r. So the question is that I want to define t restricted to omega naught. In other words, I want to define t from d omega naught to r. So you have an open set omega here, omega naught here. So how do I do that one? So if you want to, so basically the question is that in a natural way I want to restrict, because I want to understand localizing. So t is defined for all phi defined on compact support in omega. So suppose I have phi only on supported in omega naught. Can I? Of course you can define that naturally, because this is important PDEs when you are studying, because you always deal with local solutions, okay, not global solutions. So you have to have the local solutions and then we will tell. So you have to understand distributions locally and then you have to patch it. So I have to define this one, t restricted to omega with for all phi in d of omega naught. So that is very natural. So if you take phi in d omega naught, you define phi tilde as a trivial extension. We call it a trivial extension if x is by phi x, if x is in omega naught, and 0 if x is in omega minus omega naught. Note that this will be in d of omega. You have to be careful. In general, if you give a C infinity function in a small open set, an extension by 0 need not be a function C infinity function there. Okay. So you may not be able to define, for example, if you have a function like this, define minus 1 to 1 say, and this is in so this is in C infinity, no, you can make it smooth also if you want. So if you make it smooth, so if you take a smooth function like this, you can have it. So you get C infinity of minus 1 to 1, but if you extend this by 0 here, it can come very sharply here. So it may not be very sharp. This phi, if this is phi, if this is phi, this phi tilde such extension, phi tilde such extension need not be in C infinity of r. But when you have a compactly supported function minus 1 to 1, so if you have a compactly supported function, then it will not create any trouble at the boundary. So you see the trouble is at the boundary. You may not have the smoothness by extension. You can have many wave functions, discontinuity also. So this is very important to observe. So phi tilde, so when you do some simple things, you have to make sure that you are not making any fault. And then you also have the continuity, and with that continuity you can actually see that your d omega naught is continuously contained in d omega. So always see this continuous embedding when you are doing such work. So, with this your definition now T restricted to your omega naught, later we will not write restrictions, we just use the word T restricted to phi is equal to, because phi tilde is in d omega. So, T e phi tilde. Okay. This is true for all phi in d omega naught. So, you can restrict T to any given open set. Okay. So, this is the localization kind of thing you do it. Now, the next very crucial important thing, suppose you are given a partition your omega into small open set as a union, and each of, so the given any T in d omega you can restrict to any omega. The converse is about, so the question is what about converse? What about converse? Means you are given a distributions in locally in many open sets such that open sets covers your omega. Can you get a distribute? Can you patch them together? Naturally these two open sets can intersect, and at intersection two completely distributions you may not be able to do. So, you need a compatibility condition at the intersection, it should be the same basically. So, you can do that, and this is done by the famous partition of unity. So, I will just recall here partition of unity which you are already studied in your first course on PTE. If you are not, this is the time to study partition of unity. So, I will just say it partition of unity, and then maybe we will continue in the next class. Okay. These are all now what we are stretching after doing things we are developing, so that you can deal with your solutions to your partial differential equations in whatever weak formulations and all that required, which you may see it in the next lecture. Okay. So, this is partition of unity. Let omega is equal to union of omega I is in I some index set, I index set okay. Of course, omega I open in omega, okay, all are open sets here. Then I am writing the theorem itself. Then there are C infinity functions phi I is in I such that, that is the thing, three important things, three important. So, this is called locally finite partition of unity, locally finite partition of unity, such that C infinity functions phi of course defined in omega, defined on omega, such that the first property is that support of phi I is contained in omega I, okay, for all I. 2 0 less than or equal to phi I less than or equal to 1, and this is why it is called a partition of unity. I is in I is equal to 1. You have to be careful at the sum with that stage, okay, because this may be a very arbitrary summation. So, how do you add all that? But that is done by because of the third property. Maybe you can write it as third property as a second property. Then this will not have any trouble. That is support of psi I. These are all sets, compact sets in omega. I is in I, okay, is locally finite, locally finite in the sense that, so let me tell you what is the meaning of sense that for every point in omega there is a neighborhood, there is every point x in omega there is a neighborhood. You can write it in different way also, okay, both. There is a neighborhood of x which will intersect only finitely many support of phi s, only finitely many support of phi s. Okay, that's for all x in omega. The basic idea is that the support of phi is, so phi is defined everywhere in omega, so you will have a kind of thing, okay. So you can have something partitioning. So let me put my omega in a different color. Yeah, it may be inside or contained, does not matter, okay, inside that one. So it cannot intersect infinite, of course here in picture I can't show it infinitely many, but if you take support of phi will be on a subset. So you cannot have one support of phi is intersecting infinitely many support of phi. Because of that reason, for every x this will be a finite sum, will be a finite sum. That finiteness may change, it is actually a finite sum for any x in omega, okay. So these are the three important conditions, all are important. The third one is important, so that this will remain infinite. So this is localizing, okay. So basically all suppose, so you can only you can, when you have a restriction on t on omega I, you have to look for only t phi i's, okay. So I will stop this lecture, and in the next lecture we will patch them together to give a how do you patch different distributions, and then I define the singular support.